So in this video, I want to do some examples of what it means for two infinite sets to have the same cardinality. And let's consider the set of, say, the non-negative integers, just from 0, 1, 2, 3, and so on. And then let's consider that with the set E. So let's consider that with the set E, which let's say is going to be 5, 6. So this is the set of all integers greater than or equal to 5. So 5, 6, 7, 8, 9, 10, and so on. And I claim that E and the non-negative integers N have the same cardinality. In other words, I claim that there exists a bijection between the sets E and N. And whether I want to find a bijection from N to E or a bijection from E to N, those are equivalent because we know that a function, if it's a bijection, then the inverse is a bijection. So finding a bijection from one set to the other is equivalent to finding it the other way around. So I can do either way. We can either find a bijection from E to N or N to E. And let's just consider the function f going from the natural numbers to E, where f of x is x plus 5. You can check that that's clearly a bijection. It's clearly 1-to-1 and onto. Okay, I'll leave that to you to check. I think 1-to-oneness is straightforward. Onto-ness is a little bit harder to justify, but it's not hard. So you want to prove that every value in E is the image of something in N. I'll leave that to you to verify. And since there's a bijection, then, since there's a bijection, then these two sets have the same cardinality. We must be able to put them in 1-to-1 correspondence. And I think it's actually useful. I don't think it's that useful to talk about the actual rule that puts them in 1-to-1 correspondence. I think it's more useful to think about them in terms of 1-to-1 correspondence as far as the diagram goes. So let's take the numbers N, which is going to be 0, 1, 2, 3, 4, 5, and then we have 5, 6, 7, 8, 9, 10, 11, and then we're going to continue indefinitely. And we're saying that this value in N gets mapped to E, and in fact, you can also think about the inverse, so these go both ways. 1 corresponds to 6, 2 corresponds to 7, 3 corresponds to 8, and so on. And because we can put these in 1-to-1 correspondence, in other words, because there's a bijection, they must have the same number of elements, because we can match up exactly one for one element. There's one element in the natural numbers corresponds to one element in E. And you can put them in 1-to-1 correspondence. You can match them up. So there's the same number of stuff in the non-negative integers N as there is in E. Let's take that a step further. Let's prove that the non-negative integers and the integers have the same cardinality. This is a little more surprising, but it's not too surprising here. And what I want to do is I want to think about how can we count the integers? How can we put them in 1-to-1 correspondence? And so there's a few different ways to do this, and I'm going to do this in a few different ways here. But the integers are, I think actually before we go on, let me do our previous example one more way. How do we know that the set E has the same cardinality as the non-negative integers? Well, you could just count very carefully. The first element goes to 5, then 6, 7, 8, 9, 10, 11. If you go through and just systematically think about 0 goes to 5, 1 goes to 6, 2 goes to 7, the fact that every element in E gets hit at least once shows you that it's onto. The fact that it gets hit at most once shows you that it's 1-to-1, and therefore it's a bijection. So we'll do the same trick with the integers. So the integers are, let's say, -4, -3, -2, -1, 0, 1, 2, 3, 4, and so on. Okay. Didn't space these out very well. Okay, actually, let me just add commas so it's a little easier to read. Okay, and so what we want to do is we want to systematically count the integers. And so one way that we can do that is that 0 goes to 0, 1 goes to 1. And notice that we could send 2 to 2 and 3 to 3 and 4 to 4 and so on, but then that wouldn't be a bijection. Because even though it would be 1 to 1, it wouldn't be onto, because there's some values in the integers that aren't the image of any value in the domain. So in order to count a little bit more efficiently, what we'll do is we'll say 0 corresponds to 0, 1 corresponds to 1. The natural number 2 corresponds to the integer -1. The natural number, or the non-negative integer 3 corresponds to the integer 2, 4, 5, 6, and so on. 7, 8, again, and so on. And if we count that way, then everything's fine. This turns out to be a bijection. It's onto, because every integer is going to correspond to some non-negative integer. So it will be onto. It's 1 to 1 because we got every value in the integers exactly once. Okay, so here we have a function that's 1 to 1 and onto. And you can come up, again, I don't care about the rule, but the function that we have is going to map 0 to 0, 1 to 1. Here I'm thinking of this as mapping the non-negative integers to the integers. So 1 to 1, 2 to -1, 3 to 2, 4 to -2, and so on. And it's not hard to come up with the rule, it's just not very useful. It's not a good graphical way to represent that we have a 1 to 1 correspondence between these two sets.